Hello, good evening, good morning everybody. This is Paweł Sosnowski from SimScale. Welcome to this editorial demo on how to validate natural ventilation systems. It's great to have you all here. We're just about to start our demo. To confirm that everything is fine, I would greatly appreciate if you could check your GoToMeeting or GoToWebinar tool. Raise your hand if you can hear me and if you can see the screen showing this nice picture of the building being ventilated. Okay, I see some hands showing up. Great, thank you very much. Now, an organization point, there's quite a lot of us and it might be quite difficult for me to be able to answer the questions as we go. So please save them for the end of the session when we can have the Q&A in a proper way and address all the issues and all the interesting themes that you would like me to talk a little more about. So let's start our demo. First, I'll give you a short introduction of myself. As I already introduced myself, my name is Paweł Sosnowski. I am the Customer Success Engineer here at SimScale. I've been with the company almost for the whole duration since it's here. I hold a PhD in environmental and industrial fluid mechanics, and actually numerical simulations, this is my passion. I really love doing this, and it's great to have the opportunity to talk to you and present this amazing tool and the way to use it to validate natural ventilation and get benefits from running computer-aided engineering. A short overview of what we will be talking about. First, we'll talk very quickly about the benefits of using computer-aided engineering in general. Then we will go to introduce the case itself. We'll talk about the approach. Why is it valuable? How and what are we going to validate? After that, we'll talk and present the way that we prepared the case. How did we run it? Have a short demo of the platform itself and the way to make simulations like that. This will be rather brief because we want to focus on the results and the benefits that you get from running computer-aided engineering approach with your designs. And of course, we'll end up with a Q&A session where we can answer all the queries that you have. All right, so let's jump in. A few words about computer-aided engineering. Why should I care? Why should I really want to make the use of these tools? Well, most of all, because in general, creating any kind of a project is an incredibly complex process. We need to combine people from different fields with different levels of project progress. At the same time, this leads to creating these operational islands, which later may create significant difficulties in making an effective collaboration, thus hindering the project's performance. In fact, applying computer-aided engineering might allow you to reduce the risk of having this inefficient poor communication and poor planning at the very beginning of your process before you run into trouble once the stakes get really high. So, for example, you started building your building and you end up having an open door that was designed with no wind protection, and they say, well, you're not matching the standards. There's too much wind going on and ventilation running around the building. It's really late to make big changes, and it might be very expensive. All this could be avoided if you only run a simple simulation, which could take half an hour to set up, an hour to process, and there you go. So why should I care about SimScale? Because in the end, there are so many different tools that you could use in order to get your simulations done. First of all, we're accessible. You have zero hardware costs, no big machines that you need to apply and have working on your end in order to run very complex simulations. We are cost efficient. The pricing model is specifically designed for your needs and this is for everyone. Actually, I'm pretty proud of being able to work with our customers and helping them develop their workflows, which allow them to get from the very beginning of the experience with simulations and arrive to a point where they can run their own projects and make modifications, get the benefits of applying computer-aided engineering throughout the whole process. So yeah, jump in. But this is not it. Well, how does it work? Well, the only thing that you need to do is import your CAD into the geometry, and you might recognize the building that we'll be working on, set up the simulation, and finally take the design decision. And all this is done inside your web browser. No external applications. You can work from anywhere around the globe and be ready to go forward with your projects. We have incredible range of possible applications, from internal flow analysis, external flow analysis, thermal comfort, safety and contamination control, you name it. Even more, with the whole package you get access to multiple simulation types, such as structural mechanics, thermodynamics, particle phenomenon. All this comes at your doorstep whenever you need it. And the best part is you don't have to start from scratch. There are thousands of templates of simulations you can use to start your own work. But enough talking about the platform itself. So in 5 minutes I try to cut it as short as possible because most of you already know about it and you're waiting to get and talk about the project itself. So what are we talking about? Today we want to discuss the natural ventilation phenomenon, where we're trying to take advantage of physical properties of the air, the ways that it moves, the ways that it behaves around, in order to increase the ventilation inside our buildings. In most cases, the air movement is not introduced by artificial fans or blowers or any other device like this, but it's caused by the density gradients induced by temperature differences or the wind outside. And actually right now most of the building designs take that advantage of the natural ventilation combined with the effects of buoyancy-driven air motion plus forced convection to get air ventilated. It's reducing the costs and of moving the air through the building. It reduces the building total energy use and, well, increases the comfort. I mean, nobody likes to have a blower that constantly hums on top of you. At the same time, you need to take into consideration multiple elements and that might hinder your use of natural ventilation. Some of them are like the restrictions on buildings' external conditions. Let's say that you're in the middle of a busy street and, well, it's not very good to keep ventilating the whole thing with open windows. Or there's a lot of noise going on, for example, being close to an airport, even if the air quality is very good. At the same time, another thing that you end up with is that you might have a little lower control on the environment inside the building. I mean, if we end up in an extremely hot day and you want to use only natural ventilation techniques to cool the air inside of the building, it might be a big challenge. So having some artificial ventilation may also be it, but we'll see how can we validate if we are ready to do that. There are several ways to measure performance of natural ventilation. Here we mentioned some of the standards, the US standard, which is actually used around the globe to see if we are within the range of comfortable air. And for example, we know that the speed of air inside the building at the level where we are moving at should not exceed 0.2 meters per second. And in some high cases, in some very extreme cases, it should not extend 0.0 meters per second. It simply doesn't feel pleasant when you have a breeze blowing on your air. It reminds me of my old office where for some time I was sitting below a fan that was blowing air directly on me. And yes, it was nice for a while when the air was out nice and warm outside and I was being cooled. But at some point, you really get annoyed and you really feel bad. Your productivity goes down. So keeping the air speed inside a building below certain thresholds is a very important thing. And now, the second thing is making sure that you have enough air exchange inside a building. And so I would say, well, let's say that we want to ventilate the thing and we'll just keep using our natural ventilation. So there are ways to calculate this. I will not go into too deep into these equations that describe the air exchanges or the cross-wind flow rates, but basically we'll be using them later to make the calculations during the post-processing phase. Let's take a look at our case and the complexity that we are actually ready to work with. This is a 3-story shopping center with an entrance on the right side and, well, some elements. We have the boxes that represent, and some of them represent people and some represent mannequins. You can imagine that the ones that are close to those little podiums, these are the mannequins, and some of them are people. Why do we not include the models of people themselves? Well, this comes down to the approach that you need to take whenever working with computer-aided engineering. Some simplifications need to be taken. Otherwise, you get to waste a lot of time computing problems that do not benefit you. Let's imagine that I would put, let's say, a window handle, and it would be a rather small feature, but we could include it. It would be part of your CAD. On the other hand, does it really matter significantly to the general flow inside of this huge shopping center to know that there is a small vortex created behind a door handle or a window handle? The answer is obvious. Not really. This is why we're making simplifications. The same going with representing people. We want to know where they are at and how they might actually influence or feel the air moving around the whole domain. But at the same time, it doesn't matter that one guy has an arm raised or making a handshake. The general places, that's what we're actually aiming at. We will be taking a look at 5 different configurations of the ventilation system, focusing for this editorial demo only on the wind ventilation, induced wind ventilation, and we'll see what happens if we keep all the windows closed inside the domain, or if we open them on different levels. We'll have them all 3 open, starting with the ground floor, first floor, or the second floor. We'll see how does it affect the airflow inside the whole building. And we'll assume a rather not comfortable and not optimal situation where we have a breeze blowing directly perpendicular to the entrance. So the wind is just going from this direction. It will be around 5 meters per second, which corresponds to a light breeze. On one hand, it's not beneficial because, 5 meters per second is a pretty strong wind when you consider the comfort level. On the other hand, if we want to ventilate the building, the faster the wind blows, the better for us. So we might have a good exchange rate, the air exchange rate. And let's say that some would say, okay, it is enough to open the windows and open the doors to ventilate my building and make sure that everything is within the limits. How do we perform this simulation? First, we uploaded the geometry to SimScale and we set up the geometry to run the simulation. You need to take some kind of measure, a guess on how big the domain is. Usually you try to make sure that there is enough space for the wind to develop and enough place for the wind to create recirculations. At the same time, you want to make sure that the mesh, so the way that you split the domain into little pixels, which will represent the flow conditions, are fine enough. So we'll have another internal box around the building, much closer, which will improve the mesh quality there. And we'll have a better resolution of our flow fields inside. On top of that, if this was not enough, we'll make sure that the building itself is even better shown. So we'll have all the people, all the mannequins, all the lamps that are inside additionally refined to make sure that the mesh and the resolution of the later acquired solution is really, really good. And in the end, this is the result that we have. Notice how, in principle, the mesh, the general mesh, and the resolution of the flow field will be rather coarse in the bulk of the flow. This will save us a lot of computational time. Then, if we take a look at the top right picture, you can see that as we get closer to the building, we are increasing the resolution of the mesh, thus getting a better representation of the flow field. And finally, if we look at the bottom right picture, we see that the regions of interest, that is the people, let's say the small computer that is hidden behind the stairs and so on, they're resolved with even better precision that will allow us to make a good assumption and see what is actually happening inside this building. I also listed the number of cells that you get when you create meshes like this. Once more, this is a showcase to how easy it is to make a mesh once you work with a SimScale platform. The workflow that I was following in this case, I first created a mesh for all windows that were closed, and then I cloned it and used the same settings, or very similar settings, to get the rest of the meshes. So I didn't have to work on each one of them precisely. I knew that once I get a workflow that provides me with reasonable results, I could go and replicate it and run most of the cases forward. And this is actually what was happening. This is a very short overview of the simulations that were done. How long did it take me to run all of them? We will not focus too much on the details of that, but the great thing was I was running all of them in parallel. So the benefit that you get here is timeliness of your results. I can set up, in this case we have 5 different conditions for the simulation, but you can easily imagine setting up additional wind angle or checking up different wind speeds. All of them can run at the same time in the cloud. If you were running the simulations on your local machine, and let's even say that it's a very powerful thing, it has 64 cores, it has 200 gigabytes of RAM. I've seen beasts like this. Still, you would be able to run one simulation at a time. And these ones are not very long. It takes around an hour to calculate. But let's imagine that you want to have a better precision or a bigger mesh. How much time do you need to get your results? In this case, all of them run at the same time, and I get the results as they finish. So let's take a look at the results and the benefits that we get. Did we actually manage to calculate and get the proper behavior of the flow field that would allow us to use natural ventilation inside our building? Well, here we have a visualization of a flow field and how it looks like. So let's jump into the platform for a very short moment and see how do we perform this kind of visualizations. So let me just make sure that you actually can see everything. Yes. So we are inside our SimScale project. Interesting thing, you can find this project for yourselves, and you can take a look at the results, log to your SimScale account. We'll show how to do it later. And search for editorial demo, natural ventilation, department store. And you will find this as a public project available for you to see how did we actually make the calculations, how did we make the setup. This is an example of a template which I used to generate the mesh itself. The meshes are here. I will not open them because it will take quite a lot of time to load. But in principle, the workflows are really easy. You can get them through our materials that are available online, or even better, use this simulation as a template. Use it to get your ventilation simulations done and copy the settings that we're using here. Mimic them to the level that will allow you to make something similar to what has been done here. And by doing this mimicking, you can get the results in very, very quick time without getting too deep into the knowledge about simulations and about all the little tweaks that you need to make to get a working analysis. So here is a simulation workflow. I was using a rather simple simulation analysis type. This is a laminar flow, steady state, but it already gives me a good overview of what is going on inside of this problem. Adding a new simulation is also a very simple process. You simply choose the type that you want and then follow the workflow from top to the bottom, entering every leaf of this tree. At the beginning, it sounds rather daunting and complex to go through, but believe me, once you do it for a few times, you'll get so proficient that setting up a process and setting up an analysis will take you not more than 15 minutes. And I can do it from wherever I want. So we have the project loading. This is a rather big mesh, 5 million elements. We try to get a precise representation of the building itself. And then we go through all the settings, choosing the material to be the air, setting up the inlet condition, 5 meters per second blowing in the X direction, setting up the outlet. Some setup for top and bottom boundaries. And again, you can use the same settings or very similar settings to inspire your own simulations. This is the safest way to approach all these things, because like even if you get a lot of power by changing, for example, the numerical settings and so on, but at the same time, is it really what you want? To learn about what does each option do? Follow a safe pattern that already is there. Okay, and here we have the visualization of the results as they were running. You will see your job status as it goes, so you can monitor the progress of the simulation. And finally, you are able to go to the post-processor, select the solution field you want to load. I loaded it a little bit ahead of time, excuse me, so that we can have an easy visualization. So, for example, I'll make a very simple slice. We will take a slice through our domain and visualize some of the flow features. If you're interested in how to make post-processing, I highly encourage you to go to our YouTube channel. There are several very good videos on the post-processing subject, and you can get all these steps that I'm doing here explained, not to spend too much time over here, but we already see a very nice flow field around the building. The slowdown, we can visualize some elements inside of the building. Let's put the slice a little lower. There we go. Very interesting feature that already appears. Notice that I'm doing all this in the web browser. So I haven't downloaded the data yet. And we already noticed that there is a big jet entering our building, which indicates that most likely there might be a problem when it comes to having open door in a building like this with all the windows on the side of the building open. So all these windows that I hope you can see here. Maybe let me just change one option here. So make the building a little less transparent. There we have it. So all these windows are open, and we can see that, well, there is a significant jet developing inside of our our department store. On one hand, you would say, well, it's not good for the comfort of the people who are actually visiting this place. But on the other hand, one would say, hey, it's a good way to ventilate. And we can change the air inside. So let's investigate this whole problem. Okay. Let me go back and start the actual visualization. This is what I've done offline to get a little better visual techniques to visualize, but you can also follow the same steps to acquire data like that. So for example, I could add a threshold, and let's try to investigate where do we have a velocity field that is higher than 0, let's say 1 meter per second. So add a filter. And it takes a while for a big case. One more thing that we need to do beforehand. So velocity field in principle is a vector property. We would need to transform it to a scalar and then make the threshold. So believe me, all this post-processing, it seems that it takes quite a bit of time to load, but whenever you're dealing with a tool that requires significant amount of calculation, and the data that are big, I mean, this whole case is over 3 gigabytes after you unpack it and download it. So I think that loading on a screen of 3 gigabytes of data is in 5 seconds is a rather impressive thing. And the fact that you don't need to have a powerful machine to make this post-processing and visualize your flow field is another huge benefit and a thing to apply whenever working with simulations. So now I calculated the magnitude of velocity and I can plot it. There we have it. Since most of the flow field right now represents flow that is much faster than 5 meters per second, what I will do is I will show the regions where we actually have a slower field. So this will be, let's say, anything that is within the range of the acceptable range. Where do we have slow moving air inside our domain? Okay, so these are the areas. Let's make our building transparent again so that it's easier to see inside. Okay, so there is quite a lot of area where we have flow below the required 0.8 meters per second, but at the same time, there is a significant part of the building itself where we would expect to have a higher velocity. And this is not very good. Actually, now I'll jump back to this visualization where we're actually showing areas inside the building that have the magnitude of velocity above the values that are noted close to the building. So this is air moving faster than 0.2 meters per second. This is the middle top picture shows velocities of 0.8 meter per second or more, and so on and so forth. So we have velocities higher than 1.3, 1.8, 2.3, and 2.8. What do we take from seeing this? Well, definitely, if you open all three windows on all three levels, you will have a lot of motion inside of your building if you keep the doors open. So this is a no-go. You immediately know that you need to make some kind of closed environment and in order to ensure comfort for your people inside. So this is another analysis where we opened the windows on the third floor. Excuse me, this is a typo. What we have on the third floor, open windows, and again, notice that everywhere inside the building we have velocities higher than 0.2 meters per second. The second, if we open the windows on the first floor, there is a rather comfortable situation going on the top floor, but that's not enough. Most of the building has too high speeds. Moving forward, just opening the windows on the ground floor will still rise the velocity of air inside the building above 0.8, and you have significant flow of air on the floor above. So this is again a no-go. And finally, this is a situation where we actually close all the windows and keep the doors open and still allow the air to perform the ventilation. As we would expect, there is a significant recirculation or circulation of air inside the building on the bottom floor. So what do we take out of that? We need to change the setup or put some kind of construction element that will block the air from going into the building and making the recirculation happening directly. On top of that, once you download your results and you make some more post-processing, which we explain in our tutorial videos, you can actually calculate other elements like, for example, the exchange of air per hour. And in the end, even when opening all the windows, you do not get enough airflow to ventilate the whole thing. So overall, right now we know that this particular building is not very suitable for ventilation with wind or only with the wind. And we would need to install additional elements like, for example, jet fans or artificial AC units to make sure that, well, people stay comfortable and they have enough of fresh air within the thing. So some conclusions for this case. Wind ventilation can significantly affect the airflow inside the building. And only by opening the doors, we are exposing people and our guests to the effects of the air motion. If we open the windows on one side, this will not be sufficient to exchange the air inside the building. And yes, we could circulate the air, but it might be too fast, and some additional prevention should be done, should be designed in order to make sure that people like going to our building. Okay. Moving up to the final notes and a short wrap-up before we jump to our Q&A session. So why should we use the CFD? We are, thanks to that, able to make better decisions and run better simulation, better projects before we actually commit on designs, before we move it to procurement and manufacturing, before we put the walls up and we'll have to pay a lot of money to make the changes. Why should you go for SimScale? Get an accessible, easy to use, and cost-efficient tool that is for everyone. Thanks to that, you can simulate with SimScale. And who can use it? Everyone. From architects, designers, and engineers. I had the pleasure of working with many of those people and getting them onboarded, ready to run their projects. And I can tell you that this is a thing that you can work with. The way to start, go to simscale.com, start simulating in minutes. Simply click on the button, log in, create a free account. This is another amazing thing. You can start and get access to your simulations completely for free. We're giving you free access to all the features, all the simulations, all post-processing, computing power, and so on for free. The only thing we ask in return is that you share your knowledge with other people. And once you're ready to work on professional projects, get a demo, talk with our great sales department, and they will find a plan that will make sure that your data is secure, ready to work, to be worked on, and coming forward. This is the end of the presentation that I prepared for you today. I hope that you enjoyed it. I'm ready to answer any questions that you had throughout these sessions. And if you have any direct questions about this project, about the work that I did, or would like to get particular clarifications on these issues, please write me an email to me. I'll be very happy to answer. And now, let's move to the questions. We have a question that is, how was the infiltration or exfiltration rate of the building envelope modeled on the boundaries? Could you please clarify this question a little bit more? I'm not exactly sure what are you referring to. What we can do is take a look at the way that we're actually simulating in this particular process. We are simulating the whole thing. So, so can I use IFC model for this software? No, wait, I'm reading another questions. So first, let's address the way that this simulation was done. So actually, for this particular run, we have the whole flow of air being analyzed. So I have the building itself. It's standing as an it's standing as a sole thing in this big box. I'm blowing 5 meters per second of air over here from this building, and the flow is being automatically calculated. It can enter the building through the openings. I mean, right now I loaded the case where we have no where there is no actual windows, but let's hide some of this stuff. So the air can directly get in, and all the flow is being calculated, and later on, during the post-processing phase, I will be making slices, calculating the flow rates. As the flow rate goes through the opening, we'll be calculating the pressure difference in front of the door, outside of the door, checking the difference, seeing how much of it is moving through, and this way getting the data. I hope that this answers the question. Let's move to the next one. Can I use IFC model for this software? In principle, you need to use the tools that we provide. Let me see, for Revit, for example. Now, in general, for the models that you can upload, we are supporting several different formats. In general, you use the step format, IGS, STL, the native SolidWorks, Autodesk Inventor, or Rhino. When it comes to Revit, the problem with Revit is that it has its own format that is not very compliant with any other software. We plan to include Revit also as one of the next steps, so that you will be able to directly import files from Revit. But right now you would need to import it from another, export it to another format. And as far as I recall, the SolidWorks format SAT format can later be re-imported and changed to the thing that works on the platform. Get in touch with us. I actually am working with a customer who is modeling his garage. This is like a 3-story garage for industrial purposes, and he provides the CAD in Revit. We're working with that and we have a workflow for this. So, is there any kind of automatic simplification that can be done on the building's elements or context? Well, right now, SimScale focuses on what we are best at, that is simulations. And we leave the CAD modifications to the experts and people who actually work with CAD. So any simplifications that you want to work with, you need to do with your CAD software. No automatic simplifications can be done, and you actually cannot significantly modify the CAD. I mean, you can only scale it right now. We have direct integration with our great partner Onshape. If you've never heard of Onshape, the online CAD software, you should definitely check it out. So, next question: how difficult would it be to import Revit files? So there is a workflow for that, and usually you already have the possibility of exporting it. And as I said, get in touch with us, and we can provide you with a workflow on how to do it. Actually, we should make a tutorial on that. I'll make sure that it gets into the pipeline. The next question is clarification. Do you consider that the walls and windows are not perfectly sealed? Air can enter and exit the building through the walls. This is a very good question. Actually, since we are making these big simplifications, we need to take some assumptions that are required to run a simulation. And in this case, we're considering all the walls to be perfectly sealed and perfectly closed. You're 100% right. If you want to run an analysis that takes this into account, you would have to actually, there are two ways of doing that. The first way would be to actually make the small holes and mesh them, allow the flow to go through, which is not very good because you'll have an incredibly big mesh. The other approach is to create artificial inlets and outlets. So I would, for example, make a small cut that would be sucking the air out of the building, and there will be another guy that would allow the air to move in. So there is a way to model that, but in principle it's rather difficult to take this into account. Do you have a demo showing stack pressure in high-rise stairwells and elevator shafts? So definitely you can show the pressure that is building up in geometries, but like I cannot recall the case of a staircase. It is an interesting project that we could work on. So let's say that let me just load one of these cases. So basically you could definitely visualize the thing. I recall one of our customers working on an elevator shaft simulation. So this is like a rather big thing. And they were trying to see what is the flow inside such a thing. But you would have to take a look at the public project. I cannot recall it right now. Which is... yeah, so again, I see we were talking the IFC format. Definitely, we're trying to get the elements and the formats added as we go. So we take the ones that are most required, and Rhino so far was not that predominant, but this is definitely in the pipeline and will be appearing there. Another very interesting question: can we use transit analysis? And the answer is yes, of course. If you want to run a transit simulation, all you have to do is, well, create a simulation like this. Let's take a look. I would like to run an incompressible flow, for example. You could already have a preview of how many other projects are there. And all you do is you change the simulation type to transient, accept the changes. The workflow and the preparation of the simulation for transient analysis is very similar to what you do for steady state. We always try to keep things more or less the same so that you don't get lost. And once you get your hands on, it works really well. Are dynamic animated simulations possible? Yes. Well, once you get your data processed, once you get your data calculated, you can process it in a way to create animations. Unfortunately, to make actual animations, you would need to download the data and use third-party software. I have a very nice tutorial video on our YouTube channel, so do check this out. It's called Offline Post-Processing with ParaView. ParaView is an open source tool, so you can get it for free. And right now on the platform, you can only do screenshots. So another thing is infiltration and exfiltration of moisture would be another example what would be interesting to add to the model. Definitely. So for example, once the moisture has gotten behind the building's outer skin, how long would it take for the moisture to exfiltrate? Yes, this is actually a very complex problem that we're talking about, because it's not only the humidity, it's not only the wind flow that we're having, not only the temperature, but also another parameter that needs to be studied. And as you are well aware, this also involves additional phenomena such as condensation, evaporation, actual like sponge-like behavior of the building walls, and so on. So on one hand, I would think if using fluid mechanics and the flow that we have here is the way to go, because you would have to have a dedicated model on top of that to see, for example, how much moisture is inside the building and how is it being, let's say, pulled out, and how is it being dried. Actually, I was on my PhD thesis. I was working on evaporating and condensating films. So it is a pretty daunting problem. For the moment, we do not support moisture simulations and having moisture inside the air. Is there an example to show negative effect due to ventilation from small air well or long corridors very far from the windows? Definitely. This is a thing that you could do. Actually, for a problem like this, I would not run a simulation of the whole air domain around the building. I would make a much more focused analysis. So take the building itself, only inside. I would get the air well or this an open windows. I would allow them to flow out. Let's take a look. Actually, this is the public project library you can get. So this is an example of a simulation of an airflow inside a room. So you can have a focused simulation, but we can imagine having a domain that is much bigger, that has multiple rooms with open windows, with a corridor in the middle, and some kind of inlets and outlets. So definitely, this is a thing that you can do. Okay. So if you're interested in that, let us know. Get in touch with either with me or our guys through SimScale website. So let's go to simscale.com. You can start simulating in minutes. Very simple thing. And if you want to chat a little more about your problems, there is a chat function. We are available during working hours for Central Europe. And but always, whenever you leave any conversation here, we'll get back to you within 24 hours. and make sure that, well, your queries are answered. There's another question. Can this be simulated this used to simulate passive cooling, such occurs in the Middle Eastern Asian buildings? Yes, passive cooling, definitely. This is a simulation type called convective flow. We have this as a part of the solver. So you have convective heat transfer, and you can see the natural convection and buoyancy effects arising from the air being heated up. So this is another problem. For this demo, I was actually focusing on the wind, but the second thing and another simulation that you could do, even for the building that we are showing here, is the temperature, the simulation involving temperature, seeing what happens if people are standing inside and how they are heating up the air. When you're talking about Asian Middle East, we recently had an air conditioning customer who was doing an incredible project to cool one of his buildings. I can't get more details, but yes, definitely cooling like this is possible. So here, convective heat transfer, and there are multiple simulations. And again, if you look at the public project library, you can find examples of such problems. Well, we could scroll, we could look for them. Another question, two-parter, great. Do we need to model the air? In principle, yes, it is good if you have the model of the air. At the same time, you can also import your model as the solid. So it is good to have the air if possible, but at the same time, you can have obstacles in the flow and use them, for example, for external aerodynamics. Let's say that we want to see the aerodynamics of a race car. I hope that this one will load really well. We're actually having the solid object itself. So we're not getting the air domain, we're actually getting the object itself, and we'll be meshing the object and mesh around it. So yeah. The another question, can we calculate the human thermal comfort, the PMV? You cannot do it directly right now. This is a very highly requested feature, and I know that the development team is working their hours to make sure that it's available soon. Right now, you would have to get post-processing done, so get the results and do some calculation based on the fields. Because in the end, you get the thermal comfort based on the values of pressure, velocity, temperature, and so on. So you can calculate it using the results you get, but it's not a click of the button yet. Very soon it should be. Another question, will this webinar be released as a YouTube video later for sharing with other colleagues? Yes. Webinars and workshops. You can go to SimScale webinars and workshops, and here you can find quite a lot of our webinars that were done in the past. Also, this editorial demo will be part of this this list. So you go to simscale.com, learning, webinars and workshops. Another question, could you solve for forces by the airflow on the walls of an object? What does the output look like? Very interesting. Yes, you can do that. Actually, what you get is that you want to add what's called a result control item. So let's say that I would be running a simulation. I would like to see the forces acting on my building over here. I didn't set it up, but I could calculate the forces and moments. So select forces and moments, and set the center of rotation. This is necessary for the calculation, and I could simply, let's use a very simple example. I would like to see what are the forces acting, it's rotating a little, like acting on this front wall over here. So there I have it, and every 10 time steps, what you would get is a plot of the force expressed in newtons, or with other things. There is a whole section in our documentation on result control items, and you can get that. Furthermore, once you download the results, you can also make the calculation for the whole, the calculation on the results that you have. So if you forget to set up the forces at moment, there is a rather straightforward workflow that you can follow in order to get these values. So yes, and even more interestingly, you could later, for example, take some of these results and approximate them to get stress analysis. It's not it's not super easy yet, but there is a possibility. So it would be forces averaged across the wall. Could I see the point forces? So if I select this whole face, then yes, you would average you'll get the total force acting on this wall. What you can imagine is that you would, for example, create a small face on your geometry to gather information from there. This is how you are doing it directly on the platform. But if you make this calculation of the forces as a post-processing step, after getting the results and making the calculation, you can do it pointwise. For any location, any point on this geometry, wherever you have the mesh, you can get the precise value of the force acting on the wall with the precision of the mesh, obviously. Okay. I see that right now we don't have any pending questions to go for. If you still have any more, please raise your hand right now if you're typing. I see. Oh, another one. Is there a way to optimize the size of the mesh? This is an interesting topic because in principle, like, to be honest, like right now you see that I have 5 meshes over here. Believe me, it was not 5 meshes. This is a cleaned up case. I needed to make a little more. And the way that I usually approach the problem like this is I start with a rather coarse mesh to get an understanding of where are the flow features. I even run a very simple simulation on the coarse mesh. Once I see the general flow patterns, I can make additional refinements in order to improve the mesh quality. So this is the manual approach, but we are also working on having the automated meshing. You can always try to run an automatic mesh on your geometries, and in most of the cases it might produce reasonable results. So this is a very simple thing. Let's say that I would like to run a mesh for this particular problem, and you could choose hex dominant automatic wind tunnel in this case. So I would save this. We would need to select how big is our wind tunnel. In this case it's rather small, but of course I can extend it a little bit. Let's say minus 20, 20.5, 20. I'm not being very smart with this. So I set up the general domain. I choose that I want to have a fine mesh. Start running it on 32 cores. Click Start. And the meshing will commence. It will try to do a good job. Obviously, for any automatic tool, you need to expect that it might not work for a very complex geometry to apply, but it's a way to try. And once you get the simplified mesh, you can improve it, make another iteration, and get to the mesh that you actually desire. So I really believe that making a good mesh is 80% of the work for CFD, and I can see that you understand the problem and want to get it optimized, so that there are other optimizations that we are working on. Can the mesh be other than rectangular or square? Yes, you can use tetrahedral meshing for fluid flow simulations, but if you would like to use tetrahedral meshes, you need to provide the volume extract. So right now, here we have the structure. I would have to create the air domain and make the Boolean operation, so get like a negative of the geometry, and then I can mesh it with hexahedral meshings. A very nice example for that, let me just go really quickly. It's multi-phase flow analysis of a fuel tank. This is a rather this project has been around for a while, but I actually love it. Hope that the mesh loads. Yes. So we are running a fluid flow simulation on tetrahedral mesh, so irregular mesh. In fact, I personally really like tetrahedral meshes for rather complex geometries where you don't have where you have a lot of changing directions and so on. But you need to prepare the CAD in a way that you have a volume extract, not the obstacles. Okay, waiting for more questions. All right, everybody. We are already 1 hour into the session. I don't want to keep you too long. I really enjoyed this experience, and I hope that you did too. If you have any more questions, please send them to me at my email address, or you can also do that on our website. Thank you very much for your time, and I'm looking forward to seeing you simulating on SimScale platform and working with you in the future on the awesome projects that you have. For the time being, thank you very much. Have a great evening. Have a great day. Until next time. Goodbye.